Hello everyone, welcome to Pre-Lecture 19. This pre-lecture is going to cover the basics of titrations. So titration is something that you should be familiar with now based on what we've done in lab the last couple weeks. And so you should know that it is a method to determine the amount or concentration of an unknown. And so this is typically done using this sort of experimental setup where we have a burette with volume graduations on it, a way to measure our volume essentially, right? And the thing that we add to our flask is called a titrant, and it will have a known concentration, and we will know the volume that we add. We add that into our analyte. And so it can also be called a titrand, but in this class, I'm just going to call it an analyte. Typically, we start with a known volume and then probably an unknown concentration. Okay. And so in a typical titration experiment, we add a stoichiometric amount of our titrate to our analyte. We know that we add a stoichiometric amount because we're able to use something called an indicator, which of course we saw a lot of in lab last week. And this is used to determine the equivalence point. And that is, of course, the point at which the added moles of our titrant are equal to the original moles of our analyte. And so in acid-base chemistry, I will tell you in this class, and really in any class you should take, a strong acid or a strong base will always be used as our titrant, and then we will be determining the amount of acid or base in the analyte. And the acid or base in the analyte can be either a weak acid or a strong acid or a weak base or a strong base. Okay. So one of the important parts of a titration, as mentioned on the last slide, is the use of an indicator. And so this is a weak acid or base itself, and it will change color depending on whether or not it is protonated. Okay, so in this example, we have an indicator that is blue when it is protonated, and we have an indicator that is red when it is deprotonated. And depending on the pH of our solution, as it becomes more acidic, essentially we end up with a more red colored solution. Okay. Typically, you'll see this color transition within the pH range of plus or minus 1 pKa unit of our indicator. So because these indicators are weak acids themselves, they of course also then have a pKa value. And so you'll see that color transition within plus or minus 1 pH unit of our pKa. Okay. And so here's a question for you. If we had the indicator above with the colors blue when it's protonated, red when it is deprotonated, what would the color of your solution be if your pH was equal to pKa? And so take a moment, think about that. If you want to pause the video, you can. I will tell you that when our pH is equal to pKa, the solution should be purple. And that is because we would have an equal amount of our protonated indicator and an equal amount of our deprotonated indicator. So we would have equal parts red and blue, which would make things purple. Okay. And of course, we have indicators spanning a whole wide range of different pH values. So we did a lot of that, or looked at a lot of that in lab last week, but here is a chart from your textbook that has just a whole bunch of indicators and the different pH ranges that they can cover, where they transition from one color to another. Okay. All right, continuing on, I wanted to highlight a couple of important places on a titration curve, some of which, in fact, most of which you should know from lab already. Okay. So the first and maybe most important place on our titration curve is the equivalence point. Again, this is when the number of moles of titrant that are added is equal to the moles of analyte in the original solution. And for a strong acid and a strong base, so if we were performing a titration of a strong base with a strong acid, this is when our pH will be equal to 7. Okay. If we are titrating a weak base with a strong acid, then at that point our pH should be less than 7. And we'll pull up a pH curve and I can point out why that would be in just a couple of slides here. And finally, if we're using strong base to titrate a weak acid, that would of course mean that our pH is going to be greater than 7. Okay, so just want you to internalize these points before we go through some examples. The other mainly important point in our titration curve is the half equivalence point. And so as the name would indicate, this is when the number of moles of titrant added is equal to half the moles of analyte in our original solution. And at this point, our weak base and its conjugate acid are equal if we are titrating a weak base. This is also where the number of moles of weak acid would be equal to the number of moles of conjugate base that are present if we were performing a titration of a weak acid. And of course, this is also where pH is equal to pKa. Okay. All right. So let's do some examples here. Looking at this titration curve, is the titrant an acid or a base? And then is the analyte an acid or a base? And also, is the analyte strong or weak? So go ahead and take a moment, look at this, see if you can figure it out. Then we'll go through it. Okay. So this is a titration of HCl is our analyte, and our titrant is NaOH. And so the way we would know that is if we look at our x-axis is always going to be the volume of our titrant that is added. So this tells us that our titrant is NaOH. That would mean that our analyte is some sort of acid. And we know that, in fact, it's going to be a strong acid. We wouldn't necessarily know it was HCl, but we should know it's a strong acid because our equivalence point, which is the center of our titration curve here, is going to be equal to 7. And so at any point, basically, when we first start out here, we're going to be starting at a very acidic pH around 1 here. And so our hydronium will be present in excess, and then we'll very quickly, over a short addition of volume, looks like only about 1 milliliter here, go from a pH of about 2 to a pH of about 10, and then we have the rest of the way our hydroxide present in excess, okay? And again, the reason we know this is a strong acid and a strong base is because our equivalence point pH is equal to 7. Okay. All right, let's try another example. So take a look at this titration curve and same question. So is the titrant an acid or a base? Is the analyte an acid or a base? And then is the analyte strong or weak? So looking at this, we should be able to figure out that our titrant, again, is NaOH, volume of NaOH added. That means that our analyte is going to be an acid. We also know that when we have added 0 milliliters of our NaOH, we have an acidic pH, suggesting that this is an acid. And the thing that we use to determine whether this is weak or strong is our equivalence point, which is, again, the center of our titration curve here. If we look at the corresponding pH to our equivalence point, it is basic. So it is a little over 8. And because the pH is basic at the equivalence point, that means that we are titrating our analyte is a weak acid. Okay, so if we just have a general weak acid, adding NaOH, we're forming water, and then importantly, forming the conjugate base of our weak acid. And so at the equivalence point, we have used up all of our weak acid. All we have left is conjugate base. And that conjugate base can then perform a second reaction with water where it would then form a basic solution, and in this case, one with a pH around 8. Okay. So this is just kind of highlighting what I just said. Again, our initial pH, and then when we're titrating a weak acid or a weak base, before we get to our equivalence point, basically the steep slope here, we we actually have what's called a buffer range. And so it's a buffer range because we have both our weak acid and our conjugate base present. So that means that we can use our Henderson-Hasselbalch equation in order to determine our pH in this range. Okay. All right. Here is another example. So same questions. Is this is our titrant an acid or a base? Is our analyte an acid or a base? And is the analyte a strong or weak, whatever it is? And so in this case, before we add any of our titrant, which our titrant is HCl, that means that our titrant is a strong acid, and thus our analyte must be a base of some sort. So it could be a weak, it could be a strong base. If we look closer at this, though, we notice it starts off at a very basic pH. Then if we look for our equivalence point here and follow it over on the pH scale, our equivalence point has an acidic pH, right? It's below 6 here. And so that would mean that we are titrating a weak base as our analyte, okay? And in fact, we are titrating ammonia. There's no way, just based on the titration curve, necessarily you would know that this is ammonia, unless, of course, you were to find the half equivalence point and relate that to the pKa, or in this case, pKb value of NH3. But this is the equation that, or the chemical equation that's going on, where we have ammonia, NH3 plus HCl forms ammonium chloride. And so again, in this situation, at the equivalence point, we've added the same number of moles of HCl that we started with of NH3. That means that all we have left in solution is this NH4 plus, as well as chloride. And chloride, we know, won't have an effect on our pH. So our ammonium NH4 will create an acidic solution with a pH that is below 7, right? Okay. And here is, I believe, our last example of a titration curve. So what's going on here? Is our titrant an acid or a base? Is the analyte an acid or a base? And is the analyte strong or weak? And so if we look at our x-axis, this is the volume of NaOH added. So that means that our titrant is NaOH. That's a strong base. It means our analyte must be an acid. And in this case, it looks like we have kind of two plateaus here. So, or I guess three rather, where we have our starting plateau, we have this intermediate plateau, and then a final plateau. And so if we see, our pH is continually going up here. And so what we're actually looking at is a polyprotic acid. And so this would be an acid with 2 protons, where we have our first equivalence point. This would be Ka1, we could say, where we still have an acidic pH. And then we go and basically start titrating our second proton. So that would be the second chemical reaction here. And by the time we get to the second equivalence point, all we have left is the 2- version of our conjugate base, or if we wanted to include the sodium, we could say sodium disodium base. And this A here is just, of course, our conjugate base. Okay. So I hope that was informative. We'll be going through some more of the math for titration curves in class, as well as doing some examples. If you have any questions prior to then, feel free to email. Otherwise, I will see you in office hours or class. Take care.